Hey guys, what's up? So once again I welcome you all back to today's video. Today we are going to discuss another new topic named hybridization. Okay. So first of all, we should know why do we need hybridization? Why should we introduce this new topic? So for that I will go step by step and you will understand why do we need hybridization. Let us just try to figure out if I have to do the formation of BeCl2 molecule, beryllium chloride molecule, this is given to us, okay? And we have to find out how BeCl2 will be formed, what will be the shape, what will be the structure, what will be the bond angle. All those things we have to find out in detail. So let's quickly get started how to write BeCl2 structure. The first thing you have to do is to write the electronic configuration of beryllium. Beryllium, you know, so we have hydrogen, helium, lithium, beryllium. So beryllium is 4, 8. Okay, so this could be written as 1s2, 2s2. Fine. Now let us first draw the Lewis dot structure. According to Lewis dot structure, beryllium chloride should be something like this. But we don't know what are the bond lengths in BeCl bond, what will be the shape and all those things we don't know. Okay. But this is very much clear to us that beryllium has to form 2 bonds with 2 chlorine atoms. Okay. And I told you, right, in valence bond theory, we will only be using the valence shell electrons. Nothing else. We will not use the inner lying electrons because they are too deeply seated towards the nucleus that they are very attracted towards the nucleus. So they won't be available for bonding. The only thing we will use is valence shell electrons. Okay. So now let me represent it like this. So beryllium is 2s2. But we know that beryllium has to form 2 sigma bonds, and if beryllium has to form 2 sigma bonds, you should keep this thing in mind that beryllium needs 2 unpaired electrons. Am I right? This is what VBT says. VBT says that for every bond formation, you need one unpaired electron. But here beryllium is having 2 paired electrons, so it won't be able to form bonds. And if beryllium has to form 2 bonds, it needs 2 unpaired electrons. So what we do, now we say that it's okay, beryllium has 2 unpaired electrons, 2s2, but at the same time beryllium is also having 3 empty 2p orbitals. Empty 2p orbitals are there, right? So we say that why not let beryllium transfer one of its 2s electrons to 2p electrons. Okay, let this electron be excited to the higher energy level. Question number 1, ma'am, who gives this energy for excitation? And answer number 1, the energy available in environment in the atmosphere is sufficient enough to move this electron from 2s to the 2p orbital. Okay. Moreover, this energy can be compensated also. I will tell you how it is compensated after 2 minutes. Fine. So let us say beryllium goes from 2s to the 2p electron. So 1 electron is here, 1 electron is here. And this is not the ground state. However, this state we call it as ground state, and this state will be known as excited state. So we generally put this symbol asterisk in order to say beryllium is now in the excited state. Okay. Now beryllium has to have 2 unpaired electrons for bond formation. Yes, beryllium is having 2 unpaired electrons. Okay. So one electron is in S orbital and the another electron is in P orbital. Am I right? One is 2s, one is 2p. Fine. Now beryllium has to form 2 bonds with 2 chlorines. So let us now talk about chlorine. Let us go in details about what happens to chlorine. We know that chlorine is 3p5. That means chlorine is having 1 unpaired electron in 3p orbital. Fine. Now 2 such chlorines are coming. This is also 3p5. Like this. Okay. Now 1 2s of beryllium goes with 3p of chlorine and the another 2p of beryllium goes to 3p of chlorine. Let us see what kind of bond formation occurs. So if these two are combining, S and P overlapping should occur. Understood? So the bond so formed will be sp bond formed, and if 2p and 3p will combine, then the bond so formed should be 2p and 3p. Okay, can I say that one is ss bond for sp bond formation and the another is pp bond formation? This is how the VBT should work. This is how the molecule BeCl2 looks like. Okay, but now see here very carefully and try to understand the concept nicely. First of all, let me tell you what are the characteristics of S and the characteristics of P orbital. Can I say S orbital is spherical? This S stands for spherical. Yes, and I can say the P orbital is dumbbell in shaped. Quite obvious, we studied this in chapter number 2, structure of atom. I can also say that S orbital is kind of spherical and symmetrical. So this is another word I'll be adding, symmetrical. Okay, whereas P orbital is elongated in shape. It is dumbbell. One is here, very less is at the center. Right? I can also say that S is close to nucleus. And since it is close to nucleus, it will be more electronegative and at the same time it is small in size. So these all I call to be the characteristics of S orbital. Characteristics means how something looks like. So S orbital is spherical, symmetrical, close to nucleus, electronegative and small in size, right? Now let us talk about the characteristics of P orbital. P is dumbbell, P is elongated, P is thin. This is kind of a fat, ekdam healthy person, whereas P is like patla sa person which is thin. Okay. Moreover, this is far away from nucleus. And when P is far away from nucleus, I can say that this is less electronegative and this is large in size. Understood? So these are the characteristics of S, these are the characteristics of P orbitals. You might be thinking, what was the need of telling you the characteristics? Now listen to me why I told you the characteristics. S is small, P is large. So can I say that sp bond so formed will be small in size? Because it is formed from S and from P. Whereas the pp bond is formed from two large orbitals, two elongated orbitals. So can I say pp bond will be longer in size, right? And from all the informations we have got till now, if a bond is small, can't I say the bond is more stronger? And if the bond is longer, that means the bond is weaker. I hope the entire thing is clear till here. Okay, so based upon the sp characteristics, I got to know that sp bond will be small whereas pp bond will be longer, right? So according to what we predicted the structure for BeCl2, the structure should be something like this. One bond which is formed from sp overlapping and one will be the bond formed from pp overlapping. This bond should be small in size, this should be a stronger bond and this bond should be longer in size and should be a weaker bond. Understood? But if you put BeCl2 in the spectroscopic system and you try to study what is the bond length in case of BeCl2, you will be surprised to know that both the two BeCl bonds are exactly same in size, same in length and at the same time they are same in strength. Now what? Whatever we predicted till now told us that the two bonds BeCl should be different. One should be small, one should be longer, and I proved everything in front of you. But when you did experiment, you got to know the results which were like surprising, which were like totally different from what you predicted, right? So now comes the need of the term hybridization, which is the topic for today's video. Why do we need hybridization? Listen carefully. Let us go with the same procedure again. Beryllium is 1s2, 2s2. We do not consider 1s2 electrons because they are deeply seated. And 2s2 means there are 2 paired electrons. And I told you that 2p is also there, but it is empty. But beryllium has to form 2 bonds in the molecule BeCl2. Right, so beryllium needs 2 unpaired electrons. So beryllium takes energy from the surroundings, makes this electron undergo excitation. So one electron is in 2s and the other electron goes in 2p. Okay, now remember and think carefully what we did after this process. We said that 2s combines with chlorines 3p, 2p combines with chlorines 3p, right? But now I am changing my statement. I am saying rather than these two combining with 3p of chlorine, first these two mix with each other. Intermixing occurs. So can I say this is atomic orbital and can I say this is atomic orbitals? Okay, and these two atomic orbitals are actually of approximately same energy. The energy should not be like very much different from each other. They should be approximately same in energy. I am not saying exactly same. I am saying approximately same in energy. Okay. Now see, this was spherical, symmetrical, small, circular, close to the nucleus, electronegative, small in size, right? So all these characteristics I am totally taking as 100% S characters. Okay. And this 2p electron was elongated, dumbbell in shape, longer, away from nucleus, weaker, less electronegative. So let me call these characteristics as 100% p. Now let us consider a situation where I ask you to mix S and P together and see what happens. So just consider this is, let's say, a glass containing orange juice. And this is, let's say, a glass containing pineapple juice. Fine. Now I'm asking you to take a big container, pour this and this together, shake it well, mix it well. Okay. Now you pour it in 2 further glasses. Glasses should be same in size as compared to the as the initial glasses. So can I say this glass is now having 50% orange juice and 50% pineapple juice, right? Similarly, this glass is having 50% orange and 50% pineapple, right? So can I say that the new juice we got is a hybrid? Hybrid actually means a mixture. So this new juice so formed is a hybrid of these two juices, one orange and one pineapple, right? Similarly, in chemistry, I said that there is 100% S orbital, which has all the characteristics related to S orbital. We had 100% P orbital, all the characteristics of P orbital. Now, if I ask these two to merge with each other, to combine together, it leads to the formation of something which is known as hybrid orbitals. So, hybrid orbital is something which is a newly formed orbital which has characteristics of both S and P together. Understood? S is spherical, P is elongated and dumbbell. So the new orbital so formed will simply look like this. They have spherical thing also which they got from S orbital. They have dumbbell thing also which they got from P orbitals. Okay. So these two new orbitals will be hybrid orbitals. Fine. Now let me just change the marker and then I will tell you what is the use of these hybrid orbitals so formed. Let's continue. So when I tell you the use of hybrid orbitals, now see. I said that one S orbital and one P orbital, they were mixed together and they got divided into two orbitals. So these two are said to be atomic orbitals. Okay, what is the condition for atomic orbitals? That they should be approximately of same energy. How many atomic orbitals were combining? 2. So how many hybrid orbitals will be formed? Hybrid orbitals will also be 2. Okay, so this is a fact which you have to remember, that the number of hybrid orbitals formed is equal to number of atomic orbitals which are combining together. Okay, and both the hybrid orbitals so formed. Now this is very, very important. These two hybrid orbitals which are formed, they are of exactly same energy and they are of same shape. That's it. So here let me tell you the definition of hybridization, which says that hybridization is the intermixing of two atomic orbitals or more than two. So hybridization is intermixing of atomic orbitals which are of similar energy or like approximately same energy, which when combined with each other lead to the formation of same number of hybrid orbitals, and these hybrid orbitals have exactly same energy and exactly same shape. So the new orbitals formed are hybrid orbitals and the complete process is called hybridization. Understood? So this was the need why we have to go for the topic hybridization. Now see what happens. So when beryllium, okay, let us go back to where we stopped. I said beryllium star is 2s and 2p. If this combined with 3p and this combined with 3p, the bond lengths were not coming out to be same. But I said now these two combine with each other, leading to the formation of two hybrid orbitals. Okay, both of them had 1 electron initially, so put 1 electron in these two orbitals also. The number of electrons are not changing. Now try to understand. Even though I am calling them hybrid orbitals, they are not something like new or something like wow, what are they? No, orbital is basically electron cloud, right? Right? So these two hybrid orbitals so formed, they will try to arrange themselves in space in such a way that they should be maximum far away from each other. And why they should be maximum far away? So as to have minimum repulsions. Now see, this you have to start like this. This is kept here and the other hybrid orbital will be placed something like this. So this is the beryllium in the center, which is having two hybrid orbitals, each having 1 electron. Okay, so this hybrid orbital is formed by the combination of one s and one p orbital. So this kind of hybridization is called sp hybridization. Understood? Why we call it as sp hybridization? Because one s and one p orbitals are used for hybridization. This orbital is now 50% s and 50% p characters. This orbital is now 50% s and 50% p character. That means for beryllium, both the two are exactly same shape and exactly same energy. Now beryllium is like full on ready. It's like, come on, let's see who can come to beat me up. Now this chlorine comes. Chlorine, you remember, right, was 3p5, but it should have opposite spin electron. So it's like this, and the another chlorine is coming from here. This is also 3p5. Done? So what is the bond formed here? This is also chlorine. So the bond formed here is between p and sp orbitals. Okay, and what is the bond formed here? This is also sp and p. Now when both are formed by the same kind of orbitals, don't you think the bond length in BeCl will be exactly same? This is what we got from the experimental results. Okay, and if I asked you measure the angle between these two, this is 180 degree. And if the angle is 180 degree, you take a picture, the shape comes out to be linear. Fine. So this was the entire concept of hybridization, why it is required and how hybridization is useful in telling you the structure of BeCl2. Fine. So this was hybridization. Now you remember we discussed one shortcut with the formula steric number, half number of valence electrons plus atoms attached by single bond plus minus charge. Let us try to use this formula to tell a quick answer related to BeCl2. So we first write BeCl2, beryllium is 2, 2. So number of valence electrons is 2. Half 2. Number of atoms attached by single bond is 2. No charge 0. Overall 2. Remember I told you if it is 2, the hybridization will be sp. That's it. If the steric number comes out to be 2, you just mention hybridization is sp. So if hybridization is sp, you just write like this, bond angle 180 degree, shape is linear. Each bond is 50% S, 50% P, even this is 50% S, 50% P. That's it. Now see, I explained you why do we need hybridization and all the concept. Either this can be asked as a theory question, explain hybridization and its use in BeCl2 like that, or all the minute details that we studied can be asked in JEE. Fine. If you are not interested in the theory part, you just need to know the steric number, how to tell the hybridization and the shape, that's okay. Fine. So this was all about today's video where we discussed BeCl2. Next video I will be taking another molecule and I will take the use of hybridization in that molecule. So thank you very much. Bye-bye.